Hello and welcome back. In this third part of this series on respirators and the coronavirus, I'll discuss how an N95 works to remove even extremely small particles. And there is some physics involved here, but I will stick to the basic principles and ignore a lot of the nuances involved. So it should be no surprise that N95s capture particles by filtering them out of the air that you are breathing into your lungs. Depending on the brand and the various types made by a single company, they can consist of a single layer of filter material or multiple layers. But there will be at least one layer that was designed to efficiently remove particles. The filter layer is made in a process that creates a, quote, non-woven mat of fibers. That means there are no spaces between threaded fibers such as there are in the t-shirt you may be wearing. Airborne particles are trapped in this mat before reaching the airspace between your face and the mask. Here's a photo of a filter mat taken with a high-powered microscope. Note that many fibers are all jumbled together. The scale bar on the right shows how long 1 millimeter would be, and so you can see that these fibers are less than the thickness of your hair, down near 50 micrometers or less. So how does a filter capture particles? The obvious answer is that the particles simply smack into a fiber as they try to wind their way through the mat. That is true for many particles. As shown in the upper left, the air you want to breathe in will flow around a fiber strand, but the particles have too much momentum and can't make the turn and smack into the strand, the same as a car on an icy road that can't make a turn. However, there are several other forces that help capture particles. One is diffusion. This affects the tiniest particles. The gas molecules in the air literally push the particle around and right into a strand. Another significant force is electrostatic attraction. Both particles and the filter fibers are charged and can therefore be attracted to each other when they have opposite charges. The degree by which particles can be captured by a filter can be quantified by measuring the collection efficiency of the filter. Obviously, a higher efficiency means a better filter. For example, say you breathe in 100 particles in one breath through the mask you are wearing. Then let's say that 95 of the particles were captured in the mask filter. Then 95 out of 100 equals 95% efficient. But that also means that 5 out of 100 got through and were breathed in. We refer to that as the penetration, which can also be expressed as a percent. So that's not good if those 5 happen to be the virus. But the story doesn't end here in terms of what the 95 means for an N95. This is a rather nice looking graph, but potentially confusing. On the x-axis, the bottom, is the size of the particle. The x-axis is also on what is called a log scale. Using this scale essentially blows up the small end of the range of sizes so the curves can be seen better. On a true scale, the space between, say, 0.001 micrometers and 1 micrometer would be very small compared with the space between 1 and 10 micrometers, so keep that in mind. On the y-axis is filter efficiency, as was just described. So this graph shows the effect of all the forces on a particle going through a filter. Note that there are two that dominate: diffusion in the orange or reddish line, and charging, the brownish orange line. And note that diffusion causes a very high efficiency for the very small particles, and charging causes high efficiency for the large particles. As expected, impaction in green also helps to remove large particles, but not to the extent of charging the fibers. The black curvy line at the top of this graph shows the total efficiency caused by all the forces combined. This shows the filter to be essentially 100% efficient for all particle sizes, even super small viruses, except for a dip inefficiency for particles between about 0.01 and 0.1 micrometers. And getting back to this graph type for comparison, this is the same graph on a normal x-axis instead of log scale from 0 to 10 micrometers. I removed all the forces and only show the total removal, the efficiency line. Now you can see how the dip in efficiency only affects the tiniest particles, and the rest are removed with nearly a 100% efficiency. Now we have all the information needed to understand what the 95 of N95 means. As shown here, the 95% is the efficiency for the particle size that the filter is least able to remove, not all particle sizes. So the 95 does not mean that the respirator removes 90% of all particles breathed in, as implied in the exercise we went through. It means that for one particular size of all the sizes breathed in, the filter is only 95% efficient, whereas it is essentially 100% efficient. Nothing penetrates through for all other sizes. The last part of this story gets back to size and how that N95 removes the virus and the droplets the virus may be in. If we put their sizes discussed earlier on this graph, we can see that both fall in the area where the N95 is almost 100% efficient. Such a respirator should therefore be very good at removing the coronavirus before entering our lungs. And so the next part of this series will discuss whether to use a respirator or not, and if so, what kind.